Hello, seniors. Today we're gonna keep on moving with calculus, which is the last IB topic that we have left to see. And today we're gonna start with derivatives, with an introduction to derivatives. Now that you should know the concept of limits, you're gonna see how this concept of limits relates or actually defines what a derivative is about. Okay, so this is the class for today. The tangent and derivative of x to the power of n. So the objectives for today's class, first of all, define derivative using the concept of limits, interpret derivative as gradient function and as rate of change, then find the derivative of x to the power of n, and calculate the differentiation of a sum and real multiple of these functions. Okay. So let's start with some basic definitions that we're going to be applying a lot later on for the exercises and to solve problems in general involving derivatives. First of all, we have a secant line. It says a secant line to a circle intersects the circle twice. Okay, so a secant line is a line that cuts the circle, in this case, into at least 2 points. Okay. So that's secant. Then we have tangent line, which is a tangent line to a circle intersects the circle once. Okay, this is an example of a tangent line. It's like we vulgarly say le peina a la curva, right? That's a tangent line. It only touches the curve at one point. Then it says a tangent line to a curve may intersect the curve more than once. In this particular situation, you see that this line over here is tangent to the curve because, as I said before, le peina a la curva right there, right? But later on, that same line intersects the curve in another point, right? But that's fine also. The only condition for a line to be a tangent line is what I just told you, which is that the line should barely touch the curve at one specific point, right? And then I added one more definition, which is normal line. And a normal line is a line perpendicular to the tangent line at a given point. So you can see here in this graph over here, for this point over here, we have the tangent line, which is a blue one. And the normal line would be the line that is perpendicular to that tangent line in the same point, right? Perpendicular means that it forms 90 degrees, okay? So that's a normal line, just for you to remember. Okay, so let's do this short investigation to start understanding what this class is about. It says secant and tangent lines. Here's a graph of f of x equals x squared plus 1. This one over here, it's a parabola, right? Copy the graph paper and draw lines AP, BP, CP, EP, and FP. These lines are called secant lines to the graph of f of x equals x squared plus 1. Okay, so what I did is I made the same drawing. I actually copied the drawing, but make it a little bit bigger down here. And I traced these lines, AP, BP, CP, DP, EP, and FP. Okay, so that's what you see here, the green lines, right? AP, BP, CP, DP, EP, and DP again, right? So those are the lines that I am asked to trace. Then it says, copy and complete the table. So we have point P, we want to write its coordinates, so the coordinates of all the points. So by looking at the graph, for example, P is at 0, 1, right? So 0, 1. And we do the same thing for the rest of the points. A is negative 1.5, 3.25, and so on, right? You just observe the coordinates of all the points. And then we form the lines, which are the green lines I already showed you. And here, we're going to calculate the slope of each of these lines. The slope of line AP, slope of line BP, and so on. So I assume you remember how to find the slope, right? For example, here we have the formula, right? The slope of a function is always y2 minus y1 over x2 minus x1. So, for example, if we want to find the slope of line AP, we should first know the coordinates, right? Point P has coordinates 0, 1, And A has coordinates, we said, negative 1.5, comma, 3.25. So if we want to find the slope of AP, we would say this is equal to 3.25 y2 minus y1, which is 1, over x2, which is negative 1.5, minus x1, which is 0, right? If we calculate this, this would give us 2.25 divided by negative 1.5. And this 2 point, okay, this should be, apparently this should be equal to 1.5, but let's see, 2.25 divided by 1.5, yes, it's 1.5. Okay, so the slope of AP, write that here, slope of AP is 1.5, negative 1.5, sorry, negative 1.5. And that's exactly the value I wrote here, okay, negative 1.5. So we follow exactly the same process for all of the other lines formed. And what I want you to observe here is, pay attention to question 3. It says, as points on the curve get closer and closer to P, what value does the gradient of the secant line seem to be approaching? Okay, the word approaching suggests limits, right? So as you see, when we're getting closer to point P, because B is closer to P compared to A, right? C is closer to B compared to A, to B and A, right? So we're getting closer to point P, and we see that the slope, when we're getting closer, is approaching from both sides. It's approaching this value, which is slope 0, right? And if you remember, slope 0 corresponds to a horizontal line, okay? So if we draw, if we plot a point which is infinitely close to this point P over here, so infinitely close, very close, we would have a secant line, or a tangent line actually, which would have a slope of 0, right? Which corresponds to a horizontal line, okay? So that's why we relate derivatives, which we're gonna see the definition now, but that's why we relate it to limits, because we are plotting points such that we're gonna plot a point that is infinitely close to, or as close as possible to point P in order to find the derivative. Okay, so the answer to the question is that the slope approaches the value 0, as we can see here. Then part 4 says, draw the line at point P that has gradient you found in question 3. Okay, so the line should have slope 0, which is a horizontal line, which is this blue line I draw here. And this line is called tangent line to the graph f of x equals x squared plus 1 at P. Okay, so that's what I just explained. Okay, so now let's go to the concept, the most important thing. Concept. It says gradient of a tangent line and the derivative. Suppose that a point Q slides down the curve and approaches point P. So look at this situation over here. We have point P, which is, it stays there, right? It's like a fixed position. And this point Q, this one over here, we're gonna be sliding this towards point P to analyze what is happening, okay? So the secant line PQ will get closer to the tangent line at point P. As Q gets closer to P, H, which is this difference over here, becomes 0, or gets closer to 0, right? If we approach this point point Q up to here, for example, you see that the secant line would be more like the tangent line of P, and also the value of H, the new value of H, will be smaller than this original value of H, right? H is basically the distance between the x coordinate of point P and the x coordinate of point Q, okay? So That's what we're going to be doing here. We can take the limit as h approaches 0 of the gradient of the secant line to the gradient of the tangent line. And here is where the definition of derivative comes from. It's the limit when we make this value h over here approach the value 0 of this expression over here, which is basically the formula for slope or gradient of a line, okay? Let me show you why right here. I took the graph here bigger. So pay attention. If I have 2 points, Q and P, okay, I'm going to write the slopes for both. P has coordinates, sorry, not the slope, the coordinates of the points. P has coordinates, its x coordinate is x, right? And its y coordinate is f of x, right? This value over here. So that's the coordinate. The x coordinate is x and the y coordinate is f of x, okay? We're using letters only for this demonstration. And if we identify point Q, you see that point Q has coordinates. In x, it would be this value, x plus h. So that's the x coordinate, x plus h. And its y coordinate, if we look here, it's this over here, f of x plus h, right? So this is f of x plus h. We close parentheses. And yes, that's exactly what we see here. Point Q and point P. If we get, as I told you before, this value of h is just the difference between the x coordinate of point Q and the x coordinate of point P. So if we calculate the slope of PQ, which is basically this blue line you can see here, the slope of that line, we would say it's, remember the formula, y2 minus y1 divided by x2 minus x1, right? So the slope of PQ will be equal to, y2 is this, f of x plus h, minus y1, which is f of x, divided by x2, which is this value over here, x plus h, minus this value over here, which is x. So you see that here, this x simplifies with this x over here, right? So this is the same as saying that the slope of PQ, let me just copy this to save some time, is equal to, the slope of PQ is equal to f of x plus h minus f of x divided by h, right? Because the x simplifies this one with this one. Okay, and this exact formula is what we have written here, right? F of x plus h minus f of x over h. So here's the concept. If we take the value of h to the limit where h approaches 0, remember that as h approaches 0, this point Q slides up to a point where it is infinitely close to point P, right? So when we trace the line PQ, we're going to have the tangent line through point P. Okay? That's what we're doing basically. So here it says, the limit of f of x plus h minus f of x divided by h is not a constant. It is a function that gives the gradient of f at x. Okay, so here we have the definition. The function defined by the limit of f of x plus h minus f of x divided by h, which I just showed you where it comes from, when h approaches 0, is known as the derivative of f. Okay, so that's the definition of the derivative. The derivative is defined by f prime of x. This is the mathematical notation we use for derivatives. F prime of x equals the limit of this when h tends to 0 or approaches 0. Or this is another way to express the same thing. dy over dx is the same as f prime of x. It's the derivative of y with respect to x, okay? And it's the same thing, the same expression here. So here I wrote this into an easier concept that you must remember. It says derivative of a function is the gradient or slope function of the tangent line to a curve at a given point. So remember that the derivative is the gradient or slope function of a tangent line to a curve at a given point. That's the most important definition that you should remember about derivatives in order to solve the problems later on. Okay, so here it says f prime is read as the derivative of f or f prime of x, right? dy over dx is read as the derivative of y with respect to x or dy dx. Then it says recall that slope is change in y over change in x, as we just saw in the demonstration. This is expressed as delta y over delta x, right? Change in y over change in x. So the derivative of a function is just taking that difference to the limit, right? The difference between x to the limit where the difference approaches 0, right? Okay, I know this is kind of abstract, but later on you'll see with the exercises that this is a very, very mechanical and easy thing to do. Okay, so we have already seen this, and well, as I told you, the basic thing is just to slide this point point Q in order to make it closer and closer to point P until it is infinitely close to point P, and we can find the slope of the tangent line, right? So you see that these lines that I'm tracing here have already a slope which is more similar to the slope of this tangent line over here. So what I'm doing here is basically I'm reducing the value of h until it becomes infinitely small, which is when we approach this value of h to 0, what is like the definition tells us to do. Okay, so let me check if I'm not forgetting something about this. Okay, we're fine. So let's see the first set of examples. It says find the derivative of f of x equals x squared plus 1, and hence find the gradient of the tangent line when x equals 3. Okay, so we want to find the derivative. And we're going to find the derivative by applying the concept of derivative. According to the definition of derivative, the derivative is this, right? So let me write that down here. We know that the derivative of a function, f prime of x, equals the limit when h approaches 0 of f of x plus h minus f of x divided by h. This is what the definition tells us, okay? I'm not sure if this is in the formula booklet. Let me check that. If I go to the formula booklet, just a second. Here, we should go to topic 5, 6. Yes, we have the definition of the derivative here, right? A limit of this when h approaches 0. Okay, so you have the formula in the formula booklet. The definition, actually. So I'm going to identify each of these components of the formula, right? I know that f of x is a function itself, right? X squared plus 1 in this case. X squared plus 1. And we know that f of x plus h is just adding an h to wherever we have the x, right? So this would be x plus h squared. I'm plugging in the h into the x here. Plus h squared plus 1. Okay? And I'm gonna leave it like that. So if I replace these values into the formula, then I will have that f prime of x, the derivative of f of x, is the limit when h approaches 0 of f of x plus h, which is this, so x plus h squared plus 1, minus f of x, which in this example is x squared plus 1, divided by h, right, according to our formula. So if I expand this, let's see what happens. If we expand this, no, first of all, before expanding this, I need to try the limit, just as we did with the previous assignment about limits. I'm going to try replacing the h value with 0 to see what's happening. If I do that, I will have x plus 0 squared plus 1 minus 0 squared plus 1 divided by 0, right? Because we're approaching h to 0. So this gives us x squared plus, sorry, there's some mistake here. This should be in parentheses, x squared plus 1, because this negative sign is affecting all of the terms. So this would be x squared plus 1, parentheses here as well. Wait, I did something wrong here. Yes, this is x squared here. Minus x squared plus 1. There you go. So minus x squared minus 1 divided by 0, right? And here you see that x squared simplifies with x squared. They subtract each other, and the 1 gets eliminated with the other one. So this would give us 0 divided by 0. And as you know, 0 over 0 is an indetermination, right? Indetermination. That means that we need to solve this indetermination in order to find the value of the slope, right? So in order to solve the indetermination, I will expand this expression. Before actually replacing the value of h equals 0, I'm going to expand this and see what happens. So x plus h squared, if we expand this, this would give us x squared plus 2xh plus h squared plus 1, which is this term over here, minus x squared plus 1. Sorry, minus x squared minus 1 divided by h. So you see that by doing this, I can simplify some terms. For example, the x squared cancels out with this one, the 1 cancels out with this one, and here we can do a common factor of h, right? We can do a common factor of h. I'm going to take this down to have more space. There. Okay, so if I organize this, this would be equal to 2xh plus h squared divided by h. If I take a common factor of h on top, on the numerator, we will have h times 2x plus h. And here you will see that we're going to be eliminating the indetermination, right? The h cancels out with this h. So we're left with 2x plus h. And now if we try again replacing the value h with 0, now we're going to get a number which is not an indetermination, right? So this would be equal to 2x plus 0. So this gives us 2x. This will be the derivative of this function over here, okay? So let me write the complete answer. We should write it, remember we should write it this way. I'm gonna write it as, and take this down. In this case, the derivative is equal to 2x, okay? This would be an answer. You see that as we saw in the definition of derivative, let's read again the definition. It says, it is the gradient or slope function of the tangent line to a curve at a given point. Okay, so in this case, you can see that the derivative is actually a function, right? 2x. It is a function because it has the variable x. So as we give different values of x to this derivative, we're going to get different values for the derivative or the slope of the function, okay? Don't worry if you're not understanding this clearly. You'll be getting this concept more clearly later on with the exercises. So for example, if I want to find, actually that's the next question, find the gradient of the tangent line when x equals 3. If I want to know the value of the gradient of a tangent line when x equals 3 in this particular graph, in this particular graph, then the only thing I need to do is replace the value x equals 3 into my derivative function, because the derivative function represents the gradient of that function at a particular point. Okay, so what I'm going to do here is I'm going to replace f prime of 3. So I'm going to replace the value of x with 3, and this will be 2 times 3, which is 6, right? So f prime of 3 equals 6. So that is the value of the gradient of the tangent line when x equals, of this function when x equals 3. And this basically represents that if I draw, let's imagine that this is our function, and that for this point we're having x equals 3. If I trace a tangent line to that point, for that specific tangent line, its slope, the slope of this line would be 6, okay? That's what we're saying when we find this value over here, okay? So I think I'm gonna leave the class here, just not to make this video too long, and we're gonna see the other exercises in the following videos, okay? So I hope this is clear enough. If not, don't worry, we're going to be seeing more exercises about this later on, and you'll see that this will become pretty mechanical and easy to do. But it's very important for you to try to understand and keep in mind the definition of a derivative, because it has tons of applications later on. Okay, so that's it for today's video. If you have any doubts, please let me know. See you